So what we're going to do in this lecture is see why we've been looking at this idea of spectral analysis in a computer science course. So I'm going to start talking about in this lecture and the next lecture two particular applications of spectral techniques in computer science. So the first one, very famous one, and it concerns how Google's search algorithm works, Google's PageRank algorithm. So here's a bit of background to what searching for information on the World Wide Web might involve. We're looking for information on a particular subject, and the standard way we do that is we type, sometimes with voice recognition systems, so we will speak a relevant, what is called query term, and we will offer that query term to a search engine. So examples of search engines that have been around, we have the Microsoft promoted Bing, we have Yahoo, we have systems such as Ask. Roughly 25 years ago, when the World Wide Web was just becoming widely used, we had early search engines such as Lycos at Carnegie Mellon and a very important search engine called Alta Vista. Now, probably the most widely used search engine, which is pretty much replaced all of the others around, is the one that's developed by Google. How do we gauge, how do we decide which is our preferred search engine? Well, we might look at how quickly we get a response. We might be interested in the total number of results that are returned. We might be concerned with how well those results are ordered. And we might be interested in how relevant those results are. So, why is Google so popular? Why is Google so dominant amongst the available collections of search engines we might have? Well, typically, users have found that its results are returned quickly, but previous search engines did that. They've found that the results are fairly comprehensive. Previous search engines managed to do that as well. They've found that the results are relevant. Alta Vista, many other search engines managed to do that perfectly successfully. What Google adds is that the search results it returns are very well ordered. And so, while the first three criteria, these three, were realized by a number of early search engines, Google's search engine was probably the most accurate regarding these last conditions, well ordered. So, when I was using Alta Vista something like 25 odd years ago, often one found that we had to go through 70 or even 80 of the pages that were reported before one actually found one that was really relevant to the query that had been set. So what are the basic ideas that underpin search engines? We consider a selection of web pages to be organized as a directed graph. So, for example, the basic nodes of our graph might be all of the web pages we found that contain a given phrase, a given search term. And we link these pages together in the obvious way. We have a link from a node to another node if the corresponding web page points to the other web page. So the search problem that we're dealing with, that's all about ordering these nodes so that the most important appear first. Now, how do we gauge the importance of a page? Well, we might think that if a given web page is pointed to by a lot of other web pages, that fact makes the page important. There's a problem with it though. We have a naive ranking method which simply assigns a score based on the total number of links to the given page. The problem with that method is it doesn't distinguish between the sources of those links. Now, I'd like to think that my web presence is as important as Google's. It isn't. So a link from the Google homepage, a link from Microsoft homepage, in a sense, that's rather more important than a link from my personal homepage. So the naive counting method doesn't distinguish between those. So a more accurate scheme for assigning scores is to try and consider how important the source pages are, not the sources in themselves. So how do we go about building an improved scoring method for pages? Well, let's see how we can assign the score for a given page in terms of the scores that the pages which link directly to it are given. So, suppose we use this notation to denote the final score that's assigned to a given page. So what we want to do is the score that is assigned to a page, we look at all the pages that link to it, and we add up the score that has been assigned to those pages. One objection to that is it doesn't distribute the scores evenly. Any page to which links to a given page, I suppose we take the ith page, that may link to several other pages, but the score that's assigned to any page it links to is exactly the same. What we want to try and do is distribute that score out. So a page, say, that links to 20 other pages, that overall contribution ought to be divided by 20. A page that links only to one page, its overall contribution will be inherited entirely by the single page it links to. So that's suggesting that we should revise this basic scoring method and replace it with this. The score that we assign this page, we look at each of the pages that link to it, we take the score for that page, but we divide it by the total number of other pages that links to. So how do we try and model this by matrices? We can actually do this despite the fact that the expression on the previous slide looks very involved. It turns out we can model things by matrices in a fairly straightforward manner. What we have our set of pages, our set of graph nodes. We have the set of links in that structure, so the set of pages that link to another page. We're trying to compute a score vector, the score to assign to each individual page. And we're going to introduce this notation T sub I for the number of links which emanate from a given page. And so what we're trying to compute is this sum here. We're trying to compute the score for a page by summing over all of the pages that link to it of that score divided by the total number of links from it. And our score vector, this has to satisfy the relationship that when we multiply some matrix by that score vector, we get the same score vector back. Remember, we don't, when we start out, know what the score vector is going to be. So what's this matrix we're using? It's simply the entry in the ith row and jth column. Well, it's 0 if there is no link from page I to page j. Otherwise, it's this total number of links which emanate from page I, but 1 divided by that. So if there is a link, each of the total number of links is distributed evenly. So there's a very simple example. Suppose we have a world in which we only have 5 web pages, like this structure. And if we look at the matrix as results, it's this one here. So in other words, the contribution from page 1 has 2 links going out from it. They contribute a half to page 2 and a half to page 3. Page 2 only has a single link out of it, which goes to page 3. So page 3 inherits the entire ranking from page 2, whatever that turns out to be. Page 3 links to 3 pages, so its contribution is a third to each of them. Page 4 only links to 1 page. Page 5 only links to 1 page. Now, if we look at that matrix, one thing we see is we add up each of the columns, the results in each of the columns, and in every single case, that comes to 1. So what we're doing is we're going to connect this with spectral techniques that we saw earlier. And what do we find? We're looking for a score vector that satisfies this relationship with this matrix. In other words, what we say is this score vector is none other than an eigenvector for that matrix, provided that matrix has an eigenvalue of 1. And in fact, we can show that if we take any matrix which is called column stochastic, in other words, its columns add up to the value 1, then 1 is always an eigenvalue of that matrix. So for suitable graphs, in fact, that particular eigenvalue is the dominant eigenvalue. So what in effect that means is this score vector, particularly as regards the ordering of the elements in its components, that score vector is uniquely defined. So if we go back to our 5-page example, what we find is a ranking vector for those 5 pages. The first and third pages attain a score of 1, the second a score of a half, the final page a score of a third, and the fourth page 2/3. So that means that this score vector ranks the first and the third pages highest. It ranks the 5th page lowest. Now, there are some complications that can occur. One of the main problems is that sometimes one may encounter pages that don't go anywhere, so-called dangling pages. And if these are included as they stand, that means we have a column which contains only zeros, and in that case we're not going to find a suitable eigenvalue. We can adjust the matrix structure though. I'm not going to give all of the technical details. I describe some in the textbook. The other problem is some of the precise details are commercially sensitive to the operation of Google's method. The other problem which can arise is trying to manipulate outcomes by altering the link structure. So again, I give another example in the textbook. It turns out, however, that even the most basic form of Google's approach is quite resistant to naive manipulation attempts. So let me just summarize. Google's use of spectral methods dates back to work from the earliest years of the last century. And although it needs some adjustments, this dangling page problem, for example, it is a strong indication of why spectral methods are important as an application tool in computer science. They can also be adapted, in addition to this web page problem, to other types of ranking problem. I gave a few examples at the end of the previous lecture. What I'm going to move on to next, however, is a very different application, the use of spectral methods as a technique to provide image compression using this singular value decomposition approach.